This is weird. So a few days ago, they wanted me to pay extra in order to get this. Now they're giving it to me. So if you do things like that, you really don't have motivation for it. I don't know. So we'll be able to fly through chapter 5 pretty quickly because it's kind of strange, but in a way, it's kind of necessary. So whenever you've got an item that's in a mechanical system or in some sort of anything, there's ways to support it. You know, I know this doesn't look very good, but if you look at this, I mean, this is essentially a little ball that a beam is sitting on. So if the beam stretches and moves this way or moves that way, the ball doesn't really retard its motion in either direction. So in essence, it only has a vertical component of force. There's no force keeping it from moving. You can see that in bridges. There's expansion bridges that have that, so that when the heat comes on, the bridge can expand and the ground is not pushing against it to retard its expansion. Then you got pins. You can put a pin together. This time the pin will do that, but the pin can also resist like that. If someone pushes here, this pin's going to keep it from moving. That's not the case here. You push it and it just keeps rolling. So you might have a fixed support. In other words, it's kind of welded into the wall. This one you can pull down on and it'll have a moment that responds to it. I don't know what's going on with the pin system today. It's overly sensitive or something. So you can just get it close to the page. I'm not even touching it. So I don't know what's going on. So, but anyway, you've got all those. Then he starts going through all the different types of connection. There's a cable, and a cable can actually be in tension, but it can't be in compression. In other words, if you push two ends of the cable together, it's not going to supply this. The cable's not going to supply that. But if you have a link, like some sort of rod there, if it's pinned on both ends, it will respond exactly down its axis. In other words, this line is actually, I don't know if this line is actually parallel to that. So in fact, I don't even know how to, okay, so in fact, it only acts down the line itself. Both of those do. Then you can have a roller here at an angle, which means that this is the plane of movement and it's perpendicular to it. You can have a rocker, which is actually the same thing as a roller, and a rocker is more common than a roller, actually. And I can tell you why when we get a little lower down the page. You can have a smooth contact, but the chances of having a smooth contact are very, very low. If you just drop something on there, friction's going to be there no matter what. So the most logical thing to design for that actually functions is a rocker, and we'll look at that in a minute. So the thing about a contact, a roller, or a rocker is you'll notice all the forces are against the direction. If you have it in a sleeve, you can push against this wall, or you can push against that wall over here. Then you can have an actual sleeve in the other way, a rod through the middle and the sleeve going over, and what you find out is this and this are the same thing. You can have a smooth pin, which basically is a or he says a smooth pin or a hinge. which means this. Now, this is, there's a couple of these that are questionable, and we'll see those as the problems develop. This one's kind of interesting because if it is a welded piece right here and it's sliding up and down, if you twisted it like that, the bar here would undertake the moment to resist. And then, of course, a fixed support has everything that you can do. Here's a rocker, and you can see how that makes common sense. First of all, the arc here is fairly large, and if if you had it very tiny, what will happen, let's say you had a very tiny one versus a very large one, what will happen is this could actually start cracking near the surface. So that's why, the concept of this roller, it is, it behaves the same way. But if you're going to go build a roller and put several little balls in there that are small diameter and put something over the top of it, it'll work. But the fact that they're very small may start cracking the ball themselves and the surface. A rocker, the arc is kind of long, and so the chance of it cracking, there is a chance that it'll start cracking near the contact, but a lot less than if the arc of this surface was fairly small. And these pin joints, you can find them everywhere. So if you go out there and look, you'll find a lot of these, and you'll see these everywhere. And just notice that when you're moving along or driving somewhere, and you'll see this everywhere. Then he starts talking about equilibrium, because he's going to set out to do a free body diagram. There are essentially two types of forces. They're internal, and that's like the weight and center of gravity. In other words, internal means it has to do with a field around it, like the gravity field creates a weight here that sits in the centroid of the whole engine. Then there's surface of forces that are essentially the chain attached here around something. This chain is touching the surface somehow. And so somewhere, okay, so I don't know if he actually says the word surface, but that's the other. Well, he doesn't, but those are the only two types of forces you have. So you can break these down into all of this. In other words, these trusses sitting across there, their weight is an internal force, but their support is basically putting a surface force on this beam below. So they're pulling this off and saying, okay, that's a surface force going from one to the other. So when you look at this thing, he says, draw the free body diagram of that thing. So all you're doing is, a free body diagram implies that you are freeing it from its support being here, and you're going to replace it with the equivalent loads to hold it still. So what you're trying to do is sum of the forces equals 0 up here, the sum of the forces equals 0 down here as well. And this pin is very annoying, so it's, you don't have to get it close to the surface. I've never had this happen before. I don't know what's going on here. So here's a particular case in which you've got a pin, and essentially this directing force back that way. And so all you're doing is you're saying, okay, on this pin, I can have this is some type of thing that puts, well, obviously he's telling you it puts 20 pounds here, and somehow this has 30 pounds on it. And so you do the free body diagram, you break all the supports away, and you have this. Well, the next thing you do with this is you say, hey, I'm going to sum the moments about A, and that would eliminate these two forces don't create a moment about A, so you can immediately figure out the force out of that. Then you can do sum of the forces in the Y, and you'll realize these two equal, and you'll sum the forces in the X, and you'll realize this has to be 50 pounds. And so all this is basically, these problems are broken away like this. I think in this chapter, he likes you to focus on, or at least this section, to focus on the free body diagram. In other words, you have the situation, you can idealize the situation, then you essentially take the supports away, and you have this. Well, the force that touches here is this one. The force that's touching here, that's that one. And the force that's touching here, that's that one. And so he's replacing picture, the support in the picture, with the equivalent loads. So again, you got this. You're going to translate the situation. I'm assuming this is the picture. This is the drawing with all the angles and everything on it. Then you're going to get rid of this support and that support by putting the loads there. And you'll effectively work off of this diagram. So now that you have this diagram, and I don't think we're going to do that quite yet, but maybe we do. No, he doesn't do that quite yet. But at this point, you could realize, oh, if I sum the moments here, the only thing I don't know in that equation is that. Once I have that, I can sum the forces in the x and get these two will, the x component, which you'll find out, the x component of this load and this are the same. And then what you'll do with the other is you'll say, well, this one and this one and the y component here have to all equal 0. But the key is to get your free body diagram correct first. If you get that correct first and get rid of the supports, you can easily work the problem from there because you can see everything. So I think that's the 5.2. So I think that's what he's trying to do. Then in 5.3, he says, hey, now that you know how to do free body diagrams, we're going to apply this over these three equations over everything. Now, it turns out that you can end up with three equations. It doesn't necessarily have to be the sum of the forces in x and y. You can actually work your way around to have alternate sets. So what he's doing here is he's back up here. He's saying sum of the forces of the origin, which I don't see where his origin is here. That's fine. But you can come up and say, well, I'm going to sum the forces in A about point A, and then I'm going to sum the forces about point B. Those will be two independent equations because they're summing the moments. Summing the moments about A and B. They're two independent equations. Then you can just grab the third independent equation and put in there. You'll find if you pick, let's say you did this. You did sum of the moments here, 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 and here. That's four equations. But if you look at it, you will find that they're all interdependent and there's only actually three equations. So you've seen that before in math where you can have more equations, but some of them are what they're called linearly dependent on the other. And I'll actually do a couple like that. And so you can actually break it to the point where you don't do any sum of the forces, that you all just pick three distinct points on there that are not the same, and you can have three equations that way. So here the first thing he does, he takes this and he says, hey, I'm going to turn this into a free body diagram. I'm going to recognize, or I know it's hard to see, but I'm going to try the best to recognize that apparently that's a rocker on this end. I'm not sure visually he says that, but also if you look at the diagram, I can't really tell what that is, but the fact that he had no X there implies to me that looks like it had to be a rocker. This looks like a pin jointed here, and so you get those. And then, so this is essentially adding this and adding this means you turn this into a free body diagram. So now it's a free body diagram, meaning there's no supports anywhere. There's just some forces here. Now, okay, yeah, so here's your rocker. So it had to be a rocker there. But boy, you can't really tell from that picture. So first thing he does, the first thing he decides to do is sum the forces in the x. And that gives you your bx. Now you could do a couple of different things. You could, one, sum the moments about b, or sum the moments about a, or do both. So here he sums the moments about b. And what he does, he says it's 2 meters out to the 100, and it's 5 meters out to this, and then he's out here 6. So what is he doing? He's summing the moments about b. So he found bx, 645 times a little tiny 0.2. And that little tiny 0.2 is this right here. It's kind of weird. You got to kind of pay attention to those things. And then, of course, his last thing is a y, and is 7 across the whole expanse there. Now, out of that, he gets a y. And the next one, he does sum of the forces in the y. Now, I'm going to do something in addition to that. Let me see if this pen will work. My God. I might change my number. Okay, so he does sum of the forces in the y. Okay, and that's legitimate. So let's review what he's done. He's done sum of the forces in the x, sum of the moments about b, and now we're going to do something in addition to what he's done. I'm going to do sum of the moments about a. So I'm going to try my best to cram it in here. Sum of the moments about a equals 0. See the pen. I'm going to have to figure out how to go straight down with this pen, and this is not fun. So you have to dictate your positive, so I'm going to call that being positive. God, this is awful. Sum of the moments about a. Yeah. Anyway, that's positive. So this will go this way, so that is minus 0.2. Golly, 0.2 times 600 cosine 45. I'm picking the pen up. I don't know what is going on here. I'm going to have to reboot the computer before the next session. And then that's that little force. And then you got the force here that is 2 meters over. It is going in the opposite direction of what I've determined to be positive. And it is 600 sine of 45. This is very annoying. And then you got this one going this way is another minus 100 times 5. And then you got this one going this way. So it is plus by times 2, 4, 6, that's 7. Now, what I'm going to try to do is, well, I guess what I'll try to do is just work this out. But I don't have much space here. Is there anything I can do? There's nothing I can really do to so all I've got to do is take all this and divide by 7. Well, anyway, I'm just going to say what you're going to end up with is the same value. But the fact that this equation and this this is one equation, this is the second, this is the third, this is the fourth, but there's really still only three equations. And so all this is the same. I mean, they're essentially, your steps are, with this one, for example, you're going to take your free body diagram, you're going to end up with this little hook. Okay, so what he's doing is he's saying, well, the pressure that's felt here equal and opposite. Well, this is essentially going to be like that. So in other words, I'll take that rope and put it back on here. There's going to be a force. Here's going to be a force. And that's pretty much it. And then you can get in here and sum the moments about this A right here. And the distance times this, and the distance times that. It's going to tell you the first thing is that the tension is the same over the top of it. And then the second thing is you're going to figure out AX and AY. So he goes ahead, and this is probably the easiest thing to do in this particular problem, is just sum of the forces in the X. That means the X component of this is offset by that. They may not look like they're the same magnitude, but they are. And so you get that. And then the Y component here becomes large because you get 100 and then a little bit less than 100 because that, if this is 100, this is going to be a little bit less than 100. And it turns out that's like 87. And so, and all these look the same thing. Look at the part, replace it with a free body diagram, and then start to work on it. You can look right here and say, well, if I sum the moments about here, I'll have a moment. I'll have this creating a moment, and this is the thing offsetting that moment. Then once you have that, you can turn and say, well, I guess I'll sum the forces in the X. And so what you're going to get is this component is going to offset that component. And then you sum forces in the Y, and you're going to get the 60 basically sitting right down here. There is one thing extra that you did here that I should bring this up, and that is that we took our distributed load, we found the area of this, which was 80. If I pick my pen up really high, times 1.5 divided by 2. That turns out to be 60, and it's placed, okay, this is 1.5. So it can be broken into 3 chunks. And these chunks are 0.5, 0.5, and 0.5. So this is 1/3 from the heavy end, or 2/3 from the light end. And that's where you find its location. And so then he does all of his equations on this free body diagram, or related to this free body diagram. And so, I mean, this just occurs over and over and over. I don't know how many times. So maybe we'll head off and, well, let's see what the next section is. Oh, let's go ahead and do 2 3/4 members. And then what we'll do is start working some problems. So a 2/4 member is kind of something that's weird. There's only 2 forces on it. There's only 2. There's no way that this can be occurring. And there's no way this can be occurring. Why? Because, first of all, if you sum the moments about that point, there is a moment there. And the same thing here. But if you sum the moments about here, this force passes straight through that force. So that's the only situation that you can have with 2 forces. So they've got to be what they kind of like to call collinear, falling along the same line. And so that's kind of that. Now, if you have 3 force members, or 3 forces in any particular thing, somewhere, I don't know exactly where, there could be two situations. If one is tilted at all into non-parallel, so in other words, you look at it, these are parallel in that if I draw a line between them, that's supposed to be a straight line. You've got that. Anytime any one of them can cross through an origin, in other words, imagine you don't have that. And you have this, and you have this. You can put another force here to make it, you can erase this one, and then you can say, well, I'm going to put a third force on here. I could actually, let's see if I can do with my hand. That would be okay. Possibly, let me see. This one would be okay. Because you have a spot somewhere that if you sum the moments about, it goes to 0. Now, what he's done here is he's left one, left one over there. So there is a location like that. Sometimes, it's not all the time, but sometimes it's beneficial to step back and there may be an obvious location for that. Sometimes not. So this is not a given that this will always be helpful, because sometimes it's just like this and there's nothing else there. But let's say you had something like this. You had this one was supported with a pin, and say, there's my thing. I'm trying to do the best I can. Wow, that's ugly looking. And you did that. Then there's going to be some spot out here where this is going to have to go through that. So we'll look at this in a little bit more detail as we. But like I said, it's not obvious that you'll even ever really need that. It's just a recognition of something like that. So here's a member that's 2 force members, like a connecting bar. Well, okay, it's got to be pulling like that. So if it's pulling like that, you come down in here, you already know these angles, so you can just put the force straight on it. And so you simplify the problem real easy there. This, believe it or not, it's kind of weird, but this is no different than saying, why would I want the bar to look like that? Why don't I make the bar look just like this? If you make the bar look like this, eventually it might start cracking right in there. It's not going to crack along here unless you pull it really, really hard. So the key is, this is what that bar is going to experience. If you make the bar look anything different, it really doesn't matter. You can make this bar look weird, I don't know why you would want to do that, but you could do that. There's all sorts of things you could do. The forces dictate how the thing occurs. So in fact, since it's a 2 force member, that's what happens right here. And then you can just work your way out of this. Now, what does he do next? He says, hey, wait a minute. And he sort of dash till he found this. Then he has this spot at A down here, and he really doesn't think too much about it. He's just like, I'm not going to think too much about it. I'm going to have this and maybe this. But the fact that you had this one, you knew it pulled across here, and you knew this one went up here, means you know that whatever happens through A has to go up through here as well. Because the sum of the moments about this point O is 0, and there's nothing to write but 0. So that tells you that direction right off. And so, but what's odd is you really don't, okay, hang on. Wow. Okay. I don't know where. Suddenly I'm in no man's land. Where am I now? Okay. I don't know what happened there. I have no idea. Technology is getting okay. So the fact that you could look at the geometry like this, there are times that if you get really good at this, you can almost not even have to do calculations. You can just look at it and see what's going on. That's an art and a skill which takes some time to do, to get at. But you notice when he went down to this, he recognized these angles, right? He recognized everything, and his calculation became very, very simple because he recognized it. Okay, so without messing up too much, let's just pick a problem and try to do our best. Let's do 5-2, for example. And I don't know. I mean, maybe when I reboot the computer for the next class period, it'll stop doing this. I really have no idea what's going on here. It's an old computer. It is my computer. It's not the university's, so. All right. Let's just add a new page. So this one we can get away with let's try to get away with things in a similar fashion. So what we're going to do is I'm going to do a snippet of the snippet there if I can. But I'm going to use this. So what I'm going to do is just go around the edge and clip it. And then I'm going to clip it again. And then I'm going to close it out. The reason I kept this down there, I guess I clipped my distances anyway. No, I didn't. No, I didn't. No, I didn't. Okay, so if you look at this thing, okay, so let's say you want to solve it in that efficiency mode we were talking about. So chances are it's kind of here. And so chances are it kind of is like so. Okay, so, all right, now. So what did I do? Here's O, where it's going to be a moment about the zero. So let's take a look at the book and say, what actually happened here? Okay, so if you look at what actually happened here, the fact that he recognized how this all went through O meant by nature, he never really had to write a moment equation. He figured that out to begin with. So once he has the actual coordinate direction, he doesn't need but two equations. So two things, we could work this off of that, off of the assumption, and that's what we're going to do. We're going to work it one way, and then we're going to work it the other. The fact that we don't even need the moment equation, because by nature we know that if I sum the moments by O, it's all okay. So if that's the case, then of course I know this is 45 degrees. And here's what I'll try to do. I'll call this FC, for lack of a better, and then call this FA. Now I know one of them is going to be reverse. Okay, I'm drawing them both pass through O. That's not going to be the case. So, but it's okay. So what I'm going to do is I'm going to sum the forces in the y direction first. And I'm going to make this be positive. And first I get this 4. And then I get this one. Now I'm assuming, okay, so I got a -4. I'm assuming the direction to be both this way. This is not what's going to end up, but that's okay. So then I'm going to say plus FC over square root of 2. Now why is that? Well, because this is 45 degrees. There's a 1.5, 1.5. And, you know, cosine of 45 equals the sine of 45 equals to, you know, that 1 over square root of 2. And so, you know, that's that. Now this one's a little bit different because it's going to be plus FA. Now here's what I'm going to do. I'm going to sort of look at the triangle here. So if I get an FA, then it looks like to me, I go 2 times the distance to the right and 1 times the distance this way. So it's a ratio of 2 to 1, and here's the FA. Okay, well, if this is if this triangle, this is going to be square root of 2 squared is 4, and that's going to be 5, I think. Square root of 5. So in other words, this triangle is similar to this triangle right here. Okay, so that being the case, then the x component there would be FA 2 over square root of 2 would be the FA in the x direction. The FA in the y direction would be 1 over square root of 5. That's supposed to be 5. I'm going to write 2. And so that's what we're going to get there. So we're going to get, for the x direction, I'm going to get 2 over square root of 5. And then I'm done. And so now I'm going to do the sum of the forces in the x. Oh, wait a minute. I was supposed to put the y on there. So I was supposed to put that on there. So now I'm going to do the sum of the forces in the x equals 0. And this is positive. Now, all I'm going to get here is FC over square root of 2, because the x component here is that. And then I'm going to get the x component here, which that was the 2, plus 2FA over square root of 5. So the funny thing is, this is 2 equations and 2 unknowns. That's enough to solve this. I do not know. I can try. I'll tell you what, let me move the equal sign back here and move the 0 right there. And I'm going to try it. I don't know that this thing will solve that. But yeah. First of all, I've got to get it exactly in the picture. Don't know if this is going to work. First of all, let's make sure. Okay, so this shows me that FA was equal to minus 4 times the square root of 5. And then FC is equal to 8 times square root of 2. So if this thing calculated it right, and I just, I don't know what that does. Oh, okay, that makes it in case I want to edit it. Okay, close. Given the fact that that may be correct, this basically vector flips. So what we'll do now is we'll do it in a component way. And let's see if we get the same number. Now, probably the new one will end up being decimal spots. So let's do it that way. Okay. The old way, so to speak. And the old way is not recognizing 2 3/4 members. It's just doing it, just grunting through it, so to speak. So my free body diagram, here, let me get that off. Okay, wait a minute. I'm going to do a snippet of this thing so I can create a free body diagram here. So if you don't mind, I'm going to clip the support. I'm going to carry a little bit of that. I'm going to clip the support here. Oh shoot, I goofed it up. I did it backwards. Okay. So here, I will start here. Clip the support, leave it here. I'll clip the support. How do I do this? Just do it like that. That's fine. So here's the thing set up for a free body diagram. So I'm going to do it the old clunky way in which I'm going to do this, call it FC. And I'm going to do the same thing. I'm going to assume this to be in the wrong direction. I'm going to call this AX. And I'm going to call this AY. Now, I can do this. Some moments about A equaling 0 equals 2. Okay, I'll make this to be positive. Okay, so this component and this component are both FC over square root of 2. So what I'm going to do is I'm going to get this component goes this way around A, which is a positive. It's 1.5 meters over, and it's FC over square root of 2. Get all that stuff off. This component doesn't produce a moment about A, but this one does, and it's producing a moment this way, which is negative 4 times that and that to go together to give me 3. And so from that, I find FC is equal to, okay, so I get, move that over, and I get 12, okay, wait, 12 FC, wait, 12. So I'll move this 12 over, right? Let me move it over a little bit. 12. Move it over. Slip the 1.5 underneath and put the square root of 2 on top. So I'm almost hesitant to find the digits of this thing, but it says it's 8 square root of 2. Let's see. I don't know if that's what I got from the previous one. Oh, sorry. It is what I got. 8 square root of 2. So, in fact, we got it from just one. Now we're left with the AX and the AY. At this point, there's no discussion about the ratio of AX to AY. In other words, that this is twice that. So now what we're going to do is we're just going to go and find the AX and the AY. You don't really have any other choice but to use, okay, so I did that. You can do sum of the forces in the X. I don't know which one you want to do first. So you get this, FC over square root of 2, moving to the right. And then I also get my assumption moving to the right. So AX is equal to minus FC over square root of 2. Meaning this. I had a component going that way, which was FC square root of 2. And then I had this going to the right, which is AX. Now, I kind of already have FC. Okay, let's see. I guess I can go ahead and use it. Equals to minus FC. Oh, why did I do that? Let's see, 8 square root of 2 over square root of 2, where AX is equal to minus 8. Okay, I'm a little bit uncomfortable right now, but that's okay. So now we're going to work out, okay, so we did that. Now I obviously need to do sum of the forces in the Y equals 0. And you know what? I think, well, I'll just do it right here. So I get my 4, minus 4, and then I get my plus FC over square root of 2, and then I get my plus AY. So if I move everything across, I get AY is equal to, move this across, 4 minus FC over square root of 2. Don't know what that is, but that's 4 minus 8 square root of 2. Okay, so I took that and I put it right here over square root of 2, which becomes 4 minus 8, or it becomes a minus 4. Okay, the first thing is, in fact, one is twice what the other one is. So then if I want to know the magnitude of A, that would be the square root of 8 squared plus 4 squared, which would be, well, okay. Here, I'm just going to make it, I'm just going to see what it'll tell me, because you may not even recognize it's correct. It did. Okay, so that is 4 square root of 5. So that's the magnitude of A, given that I have an 8 and a minus 4. And it actually, since they're both minus, this magnitude is minus, meaning it's flipped in its direction. And if you look at that, that's what you get right here. So if you recognize your, let me put it to you like this. If you recognize this, what do you call it? This 3/4 member, you have this much calculation. You only have 2 equations to solve. If you don't recognize it, you have 3 equations to solve. And just from zooming back, I don't know, this looks like not quite twice as much calculations, but there's more calculations here than there is here. So, not sure which one you kind of like, but if you take a 2-step back and think about it, this one might lend itself to least possible encroachment of errors. The more complex it is, of course, the more chance for errors, and then the harder it is to find your errors once you've made them. Let's see. So if you look at most all of these that are in this section, they all kind of look like, there's no guarantee, but they certainly look like 3/4 members to me. For example, you got 1 here, you got 1 there. Okay, well, this will go, it'll go to here. And this is, since that's to the right, and this is down, this got to be this way. And so just like that, you got that one. This one's kind of weird. So you got this one, you're going to go this way, and this one's coming down here. Okay, so, this one's too hard of a geometry in order to get exactly right, because it looks like it may go off to the left a little bit. And so then, looks to me like you may have that. I'm not sure if it's going this way or that way. I'm not really sure. That one's a little, there's too much weird geometry there. This one, you got this. And see, the thing is of course you got that one. You don't know where this one is, but you have this moment around it. This one's going to be harder to figure out where that location is. And this one as well. So some of these are not going to fit well into that 3/4 member idea. This one will. So here's your little O. And so obviously, that may be a better way to do it. It's going to go in there like that. Now this one, probably not. Here's why. You're going to get this thing going total vertical. This thing's 1/3 over. It's going to be going vertical as well. You're left with this concept where the vertical. So the point of contact, O, where they cross each other, is infinite. In other words, they don't cross each other. They just go off next parallel to each other forever. Not much help. This one, on the other hand, kind of. So you get that, and you get this. But guess what? You think this is going to be, let's sum the moments about here. Guess what you get? If this went right through it, you got a problem because you sum the moments about this and you get this extra moment. So guess what? You have to adjust for that. Oh, that's the one we just did. I was about to say that one's. So whenever you put these moments on here, everything gets monkeyed with. So here you get this one. You get that. And then guess what? This cable bar, whatever, let me go. Pretty sure I think it's going to go like that. And then it's going through here. Gravity has you going up and down. So you got kind of a weird one there. Because now you got this one pushing on the thing. So unfortunately, you got one, you got two force, you got three force. Oh no, you got four forces. So you forget that. There is going to be a location that but you're just going to have to work it out old style there. Oh, let's see. Yeah, I'm going to have to work that one old style. Yeah, that's going to have to be done old style. I say old style, but it's kind of new to you. So anyway, we'll just go from here, and I'll do some of these problems. We'll move through this pretty quickly. Because then after that, we've got okay. Oh, 3 dimensions. That's the fun part. That'll be fun.